Students, good evening. Keep your videos on. Students, so today we'll discuss about the extraction of iron. Okay, 1 minute. Students, keep your videos on. Students, you just check this diagram first. Okay, so this is nothing but a blast furnace. You can see the name here. It is actually blast furnace, which is used for the extraction of iron. Okay, so first preliminary steps that we have discussed already, correct? Students, keep your videos on. Amog, Anaga, yes. Ashish, sorry, Anish, Ashay, Chirag, Medansh. Yes, students. Now, students, this is a blast furnace where you can extract iron. Okay. So, for the extraction of iron, first you need to add some iron ore. Okay, add iron ore. So here powder is there, so powder is obtained in the first metallurgical process, correct? So add that. Then the third main metallurgical process, their second part is nothing but reduction. Okay, so that means you have to take a coke or else carbon, add that. So this ore which contains iron, 1 minute. Okay, Amit. Yes, Medansh, okay. Anish, okay. Students, whether voice is very low? Huh?
Yes, ma'am.
1 minute. Students, so what about now? Can you hear? Is it clear? Is it high? Okay.
Yes, ma'am.
Okay. Students, for the extraction of iron, I need to prepare a iron powder. Okay, then go for the second process. If it is a hematite ore, go for hydraulic washing. If it is a magnetite, then go for magnetic separation. Okay, so this is the second main metallurgical process over. Then you convert, so depending upon the ore, students. If it is a sulfide related ore, then go for roasting, or else if it is related to some oxide, see, usually limestone, sorry, if you take Fe2O3, so it's actually oxide form, right? Fe2O3, oxide form. Once again, you heat it in such a way that you convert that Fe2O3 to FeO. So reduction of iron from FeO is easy. Okay, reduction of iron from FeO is easy according to Ellingham diagram. Students, add this ore, coke, as well as limestone is added. Why limestone is added? Limestone is nothing but calcium carbonate. Why it is added? What is the role of limestone in this case? So it removes impurity. Okay, it removes impurities which are present in this ore. For example, SiO2, if it is in contact with the, okay, SiO2, if it is in contact with the calcium carbonate, then calcium silicate will be formed, so it can be removed. So limestone, actually it's a third chemical substance. The name of the limestone, one more special name is there in the metallurgy, that is nothing but flux. Is this clear? That flux reacts with the impurity, means gang, and you can remove that as means one product will be obtained. So that product is called slag. So you can easily remove that impurity. Students, here iron extraction can be done from iron oxide at a different temperatures. Okay, different temperatures. Students, in your book, so many equations are given. So I'll club all these equations in this diagram. So in this diagram, if you study this diagram, all those reactions, so different temperatures are given, right, in your book. So all are there in the single picture here. Students, first add ore, add coke. Okay, so students, you are heating the system here. 1 minute. See, temperature is more here. You just concentrate on the hand part here. Temperature is more here. That is around 2000 Kelvin here. Correct? So this, in this area, temperature is very high, and you have to pass a blast of air. Okay, so air is to be passed. Okay, so now oxygen, so it's a very hot actually, because temperature, see, temperature here it is more, and it is moving in this direction, upward. Okay, so that oxygen reacts with this coke means what? Carbon. Correct? So that oxygen reacts with the carbon plus O2, initially you will get carbon monoxide. Is this clear, students? In the Ellingham diagram, students, I'll show that Ellingham diagram once. In this Ellingham diagram, you have already studied that for the extraction of iron from iron oxide below 1073 Kelvin temperature, you need to add carbon monoxide as a, you can add even carbon as a reducing agent, but you can also use carbon monoxide as a reducing agent below 1073, and carbon as a reducing agent above 1073. Correct? Correct? Yes. But students, did I add carbon monoxide here to this reaction chamber? No, I did not add carbon monoxide. How to get that carbon monoxide then? So carbon monoxide is formed here in this area, okay, upper region, or in this blast furnace. How? Because you are adding carbon and you are passing air. You are adding carbon and you are passing air, correct? So that carbon reacts with oxygen. That carbon reacts with oxygen. Initially, you are able to prepare carbon monoxide. Is this clear? That carbon monoxide, that carbon monoxide act as a reducing agent in lower temperature area. Is this clear? Okay. So students, now continuously oxygen supply is there, and continuously you are adding carbon. Correct? So that carbon reacts with it. Now two possibilities are there. One is carbon monoxide is formed. Okay. That carbon monoxide can also react with excess amount of oxygen. Is it right? Correct? Carbon monoxide is there, students, here, and you are passing oxygen. Okay, so here carbon monoxide, you concentrate on the hand part here in this diagram. So here carbon monoxide is there, and you are passing air here. So that carbon monoxide reacts with excess amount of oxygen to give, or else it liberates carbon dioxide. Okay, so that carbon dioxide is not required for us. Correct? Carbon dioxide, can I use that carbon dioxide as a reducing agent? No, I can't use, according to Ellingham diagram. Students, that carbon monoxide as well as carbon dioxide will be liberated. Excess carbon monoxide, students, excess carbon monoxide as well as excess carbon dioxide can be liberated. You can remove that using this exhaust. Okay, so why excess? I'm using the word excess CO, carbon monoxide. Why? Because you can use that carbon monoxide as a reducing agent below 1073. Correct? correct, according to Ellingham. So you can't use that carbon monoxide as a reducing agent above 1073 because it's a delta G value, because of its delta G value, correct, from the Ellingham diagram. Are you able to follow this, students? No response from your side. Yes. Okay. So now excess of CO as well as excess of CO2 is removed from the system. Is it okay? So now students, here you are adding, now what happens? Continuously you are passing oxygen and carbon, coke is added, ratio is there, fixed ratio for one extraction, fixed ratio is there. So that is, what is the ratio? 8 of ore, 4 of coke, and 1 of 1 ratio of this limestone. That is a fixed composition for one particular extraction. So now that carbon is there, right? So that will remain as it is below 1073. And then what happens? Reduction, it means you can extract iron from iron oxide at, means after 1073, using using carbon as a reducing agent. Okay, is this okay, students? Here this region is there, right? So this is actually a cold region actually, but temperature is very high. But with respect to this temperature range, okay, so this is a colder area, cool area. Okay, so this is little cool compared to this one. So here almost all three process will takes place, students. What are those process? First process is nothing but crushing, that is you have to do it outside. Okay, crush it and then add powder. Then concentration, so that also you have to do outside. Okay, add, wash it, and then that means hydraulic washing. If it is hematite, go for magnetic separation if it is magnetite. Then that after that you have to add that ore to this reaction chamber, blast furnace. Then see, one time reduction takes place here using carbon monoxide as a reducing agent below 1073. After 1073, carbon can be used as a reducing agent. Once again, reduction takes place. Students, I'll show you. See, I'll combine all those equations which are given separately in your book. See, different temperature, at a different temperature range, different types of reactions are possible. Students, you just concentrate on these three equations. If you start, if you start your experiment with the hematite, okay, so in the upper portion, in the cool area, okay, so or else lower temperature area, what will be there? See here, in this area, carbon monoxide will be there initially, correct? Carbon monoxide will be there initially. So that carbon monoxide, when it reacts with the hematite, you can convert that one into magnetite. Okay, hematite can be converted into, all these are possible. But you can't decide, students, here. So at the end your intention is to produce oxide. So what is the third now in this blast furnace, we are concentrating only on the third main metallurgical process. So that is nothing but conversion to oxide, after that extraction, pyrometallurgy. Is this clear? Okay, so now, students, this is a first possibility or else feasibility. Okay, so the next one, that magnetite can be converted to free metal, but students, this Fe is not pure. Okay, this Fe is not pure. Okay, so then go for electrolytic refining. Students, why I have written it as Fe? Yes, it is possible or not? Yes, it is possible, students. Why? Because you see that equation, magnetite reacts with the reducing agent, correct? So what is the form? Oxide form. Oxide form, when it reacts with the reducing agent, what is obtained? So pyrometallurgy concept, what is that? Metal is obtained, correct? Correct? Yes, that is also possible, but extraction is more economical as well as convenient from oxides, correct? So now what you have to do, you heat, or else, see, one more possible or else a feasible reaction is nothing but hematite. Even a hematite reacts with carbon and it also forms carbon, hematite reacts with carbon monoxide to give iron oxide. Okay, so this is actually third main process A. Is this clear? Okay, so but the second process is also possible because you're adding carbon monoxide, so which is a reducing agent, which act as a reducing agent at lower temperature. Is this clear, students? No response from your side. Yes, okay. Now students will go to higher temperature. Okay, so this is a, see, 500 to 800 Kelvin means it, this is the reaction which takes place here. Up to 1073 I can observe this type of reaction up to 1073, because carbon monoxide can be used as a reducing agent there. Then what
Excuse me,
happens? Yes,
ma'am. Why should we conduct the first experiment of the first equation? Directly, we can go for the third experiment, no, ma'am.
this one you're saying, huh? Yes, sir. Actually, you can concentrate on this. Actually, we are doing the same thing here. You're adding carbon monoxide, but students, I have to see, I don't have any other method to convert that Fe to O3 or else Fe3O4 to the simplified oxide form. Is this clear? Simplified oxide form. So this is the one of the method. Fourth step is there, right? Sorry. The third equation is there, right? This is the method, actual method. Okay, for the conversion of complicated oxide to the simplest oxide. So this is the third main A process. The last one is third main A process. But student, why we have to observe? Why we are observing that second process? Okay, so Anika, your question is why first and second in this case. Third is clear. Third is clear because it is a conversion to oxides. So that is third A. Why we have to use the second process, students? This reaction, see, you are adding ore. You are adding ore. So ore plus carbon is there, and blast furnace is there in such a way that you are passing oxygen. That carbon as well as this oxygen reacts with each other and it forms carbon monoxide. All these conversions takes place at lower temperature range, correct? But students, your Ellingham diagram says that you can, whenever you have carbon monoxide at a lower temperature area, suddenly reduction takes place, correct? Anyway, that iron content, iron ore is there in the oxide form only, right? It's actually in the complicated form, but it is oxide, correct? Are you able to follow, students? It is there in the complicated form, no problem. But it is a oxide. So for that oxide, if you add if you add reducing agent, you can extract metal. So that is possible there. Okay. So that is the pyrometallurgy concept. Pyrometallurgy means what? Extraction of
Ma'am,
metal. 1 minute.
ma'am, excuse.
From extraction of metal from metal oxide. Okay. Yes, sir, Shashank.
Ma'am, when we got the iron, then why are we continuing it?
Yeah.
The free form of
See,
iron.
this iron content is very, very less. Okay. So this content, so in the second process, I'll get this way Fe, right? Fe, right? So this is very, very less and then it is impure. Okay. Go for purification. That is different. So always extraction is more convenient and then yield is more whenever you use the proper method. What is that proper method? Proper method means a complicated oxide is to be converted to simple oxide, and your Ellingham diagram says that carbon is the, or else carbon is nothing but coke is the best reducing agent, correct? So therefore here for the extraction of iron you will get two types of reducing agent, carbon monoxide as well as carbon. Out of these two, if you check delta G naught value, delta G naught value is more minus, means more negative for carbon. Is this clear? So therefore their reaction rate is more, yield is more. Is it clear? Okay. Then the Fe which is formed, see, this Fe, Shashank, this Fe is formed at a lower temperature, correct? Lower temperature. Students, you just glance this picture. At a lower temperature we are not able to extract iron, correct? extract iron in the sense, students, you just concentrate on this diagram fully, completely. Where is the outlet for iron? Okay, this is the waste and this is the iron outlet. That means that iron which is formed at a lower temperature has to move down. Correct? Are able to follow? Yes. So at that time, once again air content will be there. You are passing air here. That Fe reacts with oxygen and it will be converted to FeO. Is this true? Is this true? Students, Shashank, is this clear? So imagine this is the lower temperature area. So I'm heating
So
here
we can make the outlet
outside.
before only, no, ma'am.
Okay, that setting is not like that. So these are nothing but MCF. Did you see this one MCF or else a very big industry? So container size is almost. Did you see the CFL building? Okay, so container size is this much big. So where to put the outlet? Okay, if you put outlet there in the upper part, means in the cool area, then what about the remaining content? How to remove those impurities? Okay, so that difficulty is also there. So almost all pipe connections are there in the ground level. Okay, outlet will be there in the ground level, not in the top. So most of the time, so in the big, very big container, so if this much big container is there, then here usually impurity will be there. Okay, impurity will be there in the upper layer, so that will be removed, and then iron mass is more, right? So it will settle down, so outlet is there this side. Okay, so now what happens, students? You are adding ore and limestone, coke, etc. here. So somewhere here, imagine this is nothing but so above this is below 1073. Now conversion takes place, students. I am concentrate on the video part. Okay, so here iron is there here now in the according to the second equation. So that iron oxide, when it reacts with carbon monoxide, so iron formation takes place because it is pyrometallurgy. Okay, but that iron has to come down and then you have to remove iron from here. So here what happens, what temperature is very high, 2000 something, it extends up to 2000, correct? So then you are passing air here. So when this ion comes here down, then that ion reacts with oxygen, correct? One more reaction is possible. What is that? Fe reacts with oxygen. Fe, ion which is there obtained, which was obtained in the second equation, that reacts with the oxygen here. Supply, oxygen supply is there down, correct? Correct? So it reacts. What happens? It will be converted to FeO. Possible, right? Metal plus oxygen. So generally how we will say metal, when it reacts with oxygen, metal oxides are formed. Correct? So metal oxides are formed. So whenever you get FeO, then what happens? This carbon is there, right? Coke is there, right? You're adding coke, right? Are you able to follow? So here Fe, okay, so Fe is obtained in this area and it has to be, you have to collect that Fe here. So it has to come here. So now oxygen is there. That Fe combines with oxygen to give FeO. Whenever FeO is formed, at that time the carbon acts as a reducing agent below 1007, sorry, above 1073. See the temperature here. This is more temperature, right? The temperature range is more. Okay, so below, see, you just concentrate on this diagram and then hand part. Okay, so here you will get iron, it will come down, right? So at that time it reacts with the oxygen and immediately it will be converted to FeO. Is this clear? FeO. Whenever FeO is formed at a higher temperature, carbon act as a reducing agent, correct? So immediately FeO reacts with the carbon and it will give, it gives rise to, or else you can extract metal from there. That that extraction is more economical one and convenient method. Is this clear? Is this clear? Yes. And at a very high temperature, see, iron content will come down, right? At a higher temperature, it also, see, silicon dioxide is actually a impurity which will be observed along with iron. Okay. So you have added calcium carbonate there, flux, correct? That flux, that is calcium carbonate, reacts with the silicon dioxide and you can also remove that impurity as a slag. Students, you just concentrate here in the diagram. See, Before that, I will explain this one. Okay, this is done. Then at a higher temperature, students, I have written only one temperature here, that is 900 to 1500. Okay, but you can go up to 2000 here. Okay, so what happens, students, at a higher temperature? Higher temperature, what happens? Carbon monoxide was there, correct? 1 minute, I'll show you like this. See, you have added coke, correct? You are adding air here, you are passing air. That coke combines with the oxygen and carbon monoxide is formed, correct? Carbon monoxide is formed. Students, that carbon monoxide once again reacts with excess amount of oxygen and carbon dioxide can be formed, correct? Where? In the higher temperature area. At the same time carbon added coke can also react with more amount of oxygen, correct? So carbon dioxide can be formed directly. Are you able to follow, students? Two processes are there. Added carbon reacts with oxygen and it will be converted to carbon monoxide. Over. Now, that carbon monoxide reacts with excess amount of oxygen and it will be converted to carbon dioxide. This is the first procedure, first situation. Okay. Then you're adding coke right here. Oxygen is there. You pass excess amount of more amount of oxygen. This carbon reacts with excess amount of oxygen to give carbon dioxide, correct? Students, all conversion takes place. That means either from carbon to carbon dioxide or else carbon monoxide to carbon dioxide conversion takes place in this area. Is this clear? Is this clear? Yes. Students, now at higher temperature, see, I don't want either carbon monoxide or else carbon dioxide at a higher temperature area. Okay. So both are useless for us. Now I need only coke. I need only coke. Students, when when this ion content okay, iron ore is there, right? Ion content, when it comes down, okay, it reacts with oxygen. FeO is formed. So students, but here one, yeah, you concentrate on this diagram here. Can you concentrate on this hand part now in the slide? So here one equation is there, right? FeO, the last equation. So FeO reacts with the carbon and you are going to get Fe plus CO. This is the required equation, important equation. Students, if you extract iron from this method, then the yield of iron is more. Is this clear? Okay, but here one more step is there, students. Here also we got iron, but yield of iron is less. But how to collect that iron? You have to collect that iron here. Okay, so but while see, when the iron comes down, it reacts with oxygen and it will be converted to FeO. So that FeO reacts with the coke and you are able to get Fe. Is this clear? Here content, iron content is, purity is more. Iron content, yield is also more. Students, but it is not completely pure. So you have to go for the next process, that is fourth main metallurgical process, that is nothing but refining. Yes, Anika?
Ma'am, what if ferrous oxide reacts with carbon dioxide again instead of coal?
Carbon dioxide, see, carbon dioxide does not react here because it is a gas, correct? Its volatility is more, so it will evaporate, it will be liberated here. Okay, so compared to the liberation capacity, or else see, CO as well as CO2, volatile capacity will be there, right? Volatile in the sense it's actually gas, so it liberates. So that capacity, if you consider, for carbon dioxide it is more. Students, you know that from the first volume, combustion, complete combustion as well as incomplete combustion, correct? So how to get that carbon dioxide? How to get that carbon dioxide?
Excess amount of oxygen.
Yes, complete or else incomplete combustion.
Complete combustion.
Complete, so nothing is remaining, so immediately it reacts and that much amount of gas will be liberated. It does not react once again. But what about that carbon monoxide? It is obtained by incomplete. Okay, but here that carbon monoxide which is formed is helpful for us below 1073. Okay, below 1073. So therefore, Anika, that carbon dioxide does not react with the metal. Okay, yes. Students, here you just
Ma'am,
check.
like carbon dioxide, even oxygen can evaporate, ma'am.
Yes, that possibility is there. Okay, but you have to think practically how it is. Is it true? That means temperature is very very high. Imagine. Okay, so you do one thing in Google. You just check the operating of this. Video is there. Okay, so you just check how this will be extracted. So very much a complicated process, students. It is. Okay, will you check once video part? Okay, at
Yes.
that time it will be clear to you. Yes. uh, yes, students, now you just check here at in this region, or else okay, along with this ore, along with this ore is not a, yes, ore is concentrated. Correct. Second main metallurgical process is done. So now we are concentrating on the third step. Concentrated, but still impurities will be there. So what type of impurity will be there? Maximum amount of impurities are removed in hydraulic washing or else in the magnetic separation. But you can get even silicon dioxide type of impurity. See, students, so you hear one more equation is there. Calcium carbonate, so that is a limestone. It combines with the SiO2. It combines with SiO2. So how this process takes place? See, you just concentrate on these two equations. Calcium carbonate dissociates to give. Students, why it dissociates? Because temperature is very high. When temperature is very high, at that time, calcium carbonate decomposes to give the corresponding calcium oxide plus carbon dioxide. Once again, that carbon dioxide is exhausted. You can remove through exhauster. Now, this calcium oxide reacts with the silicon dioxide. So you can remove that in the form of calcium carbonate. So each and every maximum impurities are removed, right? Maximum impurities are removed in concentration, and silicon dioxide type of impurities are removed by the addition of flux as slag. Is this clear? Okay. Now, students, the main process of this is nothing but the last equation which is there along with this diagram. So that is EFEO, that is iron oxide. From this iron oxide, you can extract metal, that is iron, with the addition of coke, carbon. Is this clear? Yes, students. Now, 1 minute. 1 minute, students. Now, students, I have how to remove this slag. How to remove this slag? Yes, Ketan, any doubt?
Ma'am, all these reactions are very quick, right? Because
Yes.
the ore just falls from the top and just it refines and it comes down.
Yes. And see, usually in the industry, this they will never see. Actually, temperature is there, right? Temperature in the bottom portion of the blast is always high. They will not switch off. Okay, it is a continuous process. Continuous process. So somewhere in the from mining area, that a content will come and then it will fall in one chamber. So there, what happens? Grinding takes place. Okay, you can grind it. Okay, grind mixture will be there. It's that setup is called mixture. Then it will be washed in another tank. You see the this one process. Okay, it is there. That will be washed. Okay, and then it will be converted, it will be passed to the another chamber. So which one? So that impurity will be removed, and then iron content will be transferred to another chamber's size is almost this building size. Okay, so and then their continuous heating will be there. So at the end you can add, means at the end means third process is there, right? So for that you have to add this content to the furnace. Okay, blast furnace. Temperature is always high and then machines are running always, all 365 days. So 24 by 7. Okay, yes. So temperature is very high. This reaction takes place continuously. Okay, so to explain in book, this type of diagram is given, but it is a very big system. And at the end, students, I'll concentrate on this now. At the end, you will get iron. Along with that, students, you have impurity. How to remove that impurity? Okay, so what type of impurities are there? 1 minute. Yes, students, dust particles or else any other mud particles you can remove in the first another chamber, not in this blast furnace. Okay, so many furnace will be there, means container will be there you can remove. That is nothing but second step. So now in this blast furnace, how to remove, what to remove? You have to remove silicon dioxide impurity. SiO2 is there, right? That you have to remove. Or else some other contaminant, if it is there, that you have to remove. See here, calcium silicate is formed, students. Correct? So that is nothing but a slag. So it's in the molten state. Okay, calcium oxide is actually solid and silicon dioxide is also solid. Students, this calcium oxide as well as silicon, yes, Nihal?
Ma'am, at what temperature the reaction of calcium oxide with that silicon
Yes,
dioxide
silicon
takes place,
dioxide.
ma'am?
It is after 1073. It can take place anyway. Okay, so before this, okay, before this 1073, see here, uh, that means it depends upon the amount of SiO2 which is present. Students, in this explanation, we will take that 1 ratio of limestone is added. Correct? We have taken like that. But in the industry, it is not like that, students. Correct? So you have to, so this is actually a commercial extraction. So you need to add so many, you need to take more amount, or else a ratio will be more. Correct? So therefore, at this temperature, means above 1000, sorry, 1070. Okay, above 1070, this, that means temperature when it increases, at that time you can convert that solid state to liquid. Okay, when temperature is more, solid converts to liquid. Students, there is a specific temperature for calcium oxide. That means it converts, sorry, it reacts with SiO2 and it converts to it will be yeah, converted to SiO2, sorry, calcium silicate, that is CaSiO3, and that is to be converted to molten state. Okay, so when Nihat, when temperature is more than 1070, okay, calcium oxide, sorry, carbon dioxide, sorry, calcium carbonate you have added. Correct? Correct? So after 1073, that calcium carbonate dissociates to give calcium oxide as well as SiO2. Over. Then that calcium oxide has to react with SiO2. Correct? So then it has to produce a calcium silicate. Then it has to melt. At that time, temperature increases. Is this clear? So now, is this clear, Nihal?
Yes, ma'am.
Okay, so now this slag, I have to remove this slag. So you can remove this here, solid waste. Okay, so from this, see how you have to extract iron, right? You will not get iron rod or else a solid iron. It will be there in the molten state. Okay, so you see the video in Google. Okay, so it will be there in the melt state, molten state. So from that molten state, if you compare the molten state of iron as well as the melt state of that calcium silicate, then that will be a very means easy to remove. That slag easily removed from the melt of iron. Okay, so you collect all unwanted substance here, that is solid waste. Over. Then what you want? You want to collect a pure iron, right? But what is written here, students? It is written as a pig iron. Correct? It is written as a pig iron. What do you mean by pig? Pig is a dirty. Correct? That means this iron is also contains some amount of impurity. Students, you note on this. Okay, so the iron which is extracted after iron which is extracted from this blast furnace, the name of that iron is nothing but a pig iron. Did you note down that? Did you write? Students, keep your videos on.
Excuse me, ma'am.
Yes.
Ma'am, are there chances that molten slag and molten iron might mix
No.
at the temperature stable?
Because see, if you change the ratio, it is possible. Okay, so you are taking ore in a large quantity, but you are adding a calcium carbonate in a lesser quantity. Why it is so? Because sometimes scientists did the experiment, correct, and they found that okay, small amount of impurity will be there, one thing. And your knowledge says that, Anika, in the second step a maximum amount of impurities are removed, correct. If you avoid that second process, then there is a chance. Okay, at that time you will get more amount of impurity, more amount of impurity. Is this clear? Okay, at that time the iron may mix with that, correct. Yes, Ketan.
Ma'am, will the iron ore or whatever molten iron will go to that from where the air is coming?
No. Okay, yeah. So your question is correct. That is something, but in this diagram it looks like that. So there is a gap, so it may fall here. No, the system setup will not be there like this. Okay. So air, Ketan, are you from Mangalore?
No, ma'am.
No. Okay. So you just see the setup. How to say? Have you seen chimneys?
Yes, ma'am.
Ah, so there actually some space will be there, right? So at that time, see, the side tube will be there. Okay, tube will be there, but a solid substance cannot come from that. Uh, what you have to say, that chimneys or else some what gap. Okay, is this clear?
Yes, ma'am.
Solid substance cannot come. There is a see, actually I have seen the system, iron extraction system there. Actually mesh will be there. So mesh in the sense, see up, can you see this one
Yes, ma'am.
this type of thing will be there. That means you have to pass a pure air. Okay, so that is also that type of a purifier will be there in that. Because see students, here we need to pass only oxygen actually. Correct. For the combustion process, we need oxygen. See, blast of air and oxygen. Why it is specifically written it as written as oxygen? Students, you may get another reaction. So nitrogen, if it is there, you will get some metal nitrides, something. Correct. So there will be a filter so that a solid substance will not enter into that. Okay. But in this diagram, there is a gap. So you may feel that this may leak. No. Okay. Yes. Students, now you collect this molten iron, okay, from this blast furnace. So that molten iron is called pig iron. Why it is pig? Students, you just write that molten iron contains impurity. It contains impurity. Okay, it is not pure. But even though you got more yield of iron is obtained in this method, but that is not pure. So students, it contains a 4% of carbon. So students, write pig iron and its composition. You write pig iron, put hyphen and write its composition. I can't write in this. You have to write. Okay. So you just write 4% carbon, and you will have many more impurities. Okay, so what are those impurities which are present in pig iron? So that is nothing but, you just note down, sulfur may be there, sulfur, phosphorus, silicon, as well as manganese. These are all the impurities which are there in the ore. Okay, so is this clear, students? Pig iron composition is very important. It contains 4% carbon and phosphorus, sulfur, silicon, manganese as a impurity, small amount of impurity. Is this okay? Now students, you take that pig iron. Okay, you take that pig iron and then heat it. Okay, so you want to, do you want, yes, Anihad?
What is the principle based on the separation of pig iron and
Huh.
slag, ma'am?
Okay, slag is actually lightweight here. Okay, silica means what? Students, silicon dioxide, silica. Do you know? So in sand, some aluminum part. Okay, did you check that white part? Huh? No, no.
Yes, ma'am.
Usually, 1 minute. Yes, students. Now you concentrate on this pig iron. So what we are discussing, I think, related to this solid waste, right? Yes. So students, melt. Yes, Nihad, you have asked this question, right? Melt of iron. Its density is more. Okay, mass is more. Students, keep your videos on. Students, students, keep your videos on. Okay. Yeah. Now, students, here solid waste will be there, right? The silica, its weight is less. Silicon dioxide is there, right? Its weight is less. So, with respect to this melt of iron, since its weight is less, so it will be removed first. Is this clear?
Yes, ma'am.
Yes. Therefore, Nihada and all other students, you just concentrate on the outlet here. So, this solid waste, you can collect it first. You can, this solid waste, you can collect it first because its density is less, so therefore its opening is there up, correct? And density of this iron is more, so it will settle down. Okay, it will settle down, so that will be collected here. Students, here molten iron is written, right? So that will come from here to here. Okay, so you just concentrate on this part, hand part. So it will come from this side to this side, okay, from here to here. But the thing is, so here the density of the impurity is less, so it will be collected first. And density of the pig iron means iron density is more, so it will be collected later. So you just concentrate on the opening. It is there up, and this is down. Yes, students, and now coming to the pig iron. Pig iron is the one which contains a more amount of impurity. Okay, 4% of impurity. Okay. So now, students, if I add in the extra, see, you consider you take one gold, or if I add some amount of impurity, will you agree? No. Same thing in case of iron. Maybe value is not there with respect to that gold, okay, in front of that gold, but it has its own value, correct? So we have to extract metal in its pure form, correct? So students, and now what I had to do? I had to reduce the impurity. Okay, but I can't remove all impurity because we are in third stage. Okay, you can remove 98 or else you can purify 90%, 99%, or else 100% pure iron can be obtained at the fourth step. Okay, that is a refining step, but this is the third step. Okay, so what we are discussing, this is only the third step. So students, how to convert that pig iron into the purest form? So what you have to do, you take that pig iron and then heat it. Okay, take that pig iron and heat. Okay, so that means in industry, that pig iron will be transferred to another chamber. So there they will heat it. Okay, then carbon content, right? Heating, say students, pig iron means 4% of carbon content is there. So you shift that pig iron to another chamber and then heat that particular chamber. What happens? Heating means oxygen supply will be there once again, correct? Correct. So now what happens, that carbon reacts with oxygen and then some amount of carbon dioxide or else carbon monoxide will be liberated. Okay, but if you do this method, you can reduce only 1% of carbon content. Is this clear, students? Next you write a pig iron, you write pig iron, put hyphen, pig iron, put hyphen, heat it, right? It pig iron, then write hyphen, then write heat it. So we will get cast iron, CAST. Cast iron is obtained. How to get cast iron? By heating pig iron. Okay, we'll get cast iron. Students, so what do you mean by cast iron? Cast iron is the one where you have decreased carbon content, only that much. Okay. Now you write cast iron composition. Students, I'll repeat. Pig iron is the outlet from blast furnace, which contains 4% carbon, sulfur as an impurity, phosphorus will be there as an impurity, silicon will be there, as well as some other manganese particle will be there. Now we don't want that impurity. You heat it. Okay. So that pig iron will be converted to one more form. So that form is called cast iron. CAST, cast iron. What is the composition of cast iron? Cast iron is the one where you have decreased the carbon content. So cast iron contains 3% carbon. Remember, cast iron contains 3% of carbon. Then it is a little hard compared to that of the pig. Cast iron. Amit, are you concentrating? What I have explained now, just now, tell me. Don't send message. You have to unmute and then tell me.
Little internet problem over there. I was checking the modem, ma'am.
Okay. But process, did you get the process?
Yes, ma'am.
Okay. Yes, students. Now you take that pig iron and then heat it. Okay. You can remove maximum amount of carbon dioxide, or else you can reduce the carbon content by only by 1%. Okay. So now you will get a cast iron where the percentage of carbon content is nothing but just 3%. Over. What about that sulfur, phosphorus, manganese? If it reacts with oxygen, you can remove that. Okay, at a higher temperature. If it reacts with that oxygen, okay, it will be removed. Exhausted will be there, it will be exhausted in the form of oxide. No problem. Okay, so if it is remaining, then you can purify it in the fourth step. Is this clear? Yes. Students, but that cast iron is also having some problem. 3% of carbon is there, right? I don't want that much of amount of impurity. So once again you write, students, next you write, take a cast iron and then once again you heat it. Pig iron, heat it, you will get cast iron. Take cast iron, heat it. Then students, you will get wrought iron. Wrought iron, spelling WROUGHT. Wrought iron.
Excuse me, ma'am.
WROUGHT. Okay.
Excuse me, ma'am.
Yes.
Ma'am, will it be in the form of oxide? Like when we heat it, will it form oxide or it will be iron only?
Which one?
Like we heat the pig iron
Huh.
and it
Pig
forms
iron in the
cast iron.
no. Pig iron, cast iron will be there in the iron form now, not in the oxide form, because that our reduction is already done. Okay. So outlet, what we got in the outlet is nothing but just a metal. Okay. So reducing part, it is already done in the blast furnace. Okay, Satvika.
Okay, ma'am. Like when we heat it, it will
When we
be iron.
iron does not react at that time, only the impurity part is there, right? Okay, so if you check the melting point of iron, it is nearly 1500 something. Okay, 500, 1500. So that much of heat is not supplied. Okay, so students, in pig iron, iron will be there in the iron form only, not in the oxide form, because that reduction is done in the blast furnace. Over, finished. Now, since it contains 4% of carbon, now you have to heat it. For carbon, little amount of oxygen is enough. Okay, you need not to heat at around 1500. Okay, melting point of iron is 1500. At that time only it reacts, melts. It will be converted to another state. Okay, so that much of temperature is not required. So you apply little amount of oxygen with a particular temperature, then carbon can be converted to carbon dioxide and then it will be liberated. Is this clear? You will get cast iron. But cast iron contains 3% of carbon as an impurity. So once again you heat it. Once again, carbon reacts with oxygen. Once again you can remove carbon dioxide. Is this
What
clear?
is the use of repeating these things?
So you can remove carbon content, only that much.
No, how does it change things? What like what if we heat everything the same time itself?
Water?
Like instead of doing things twice, can't we
Huh.
just heat it at one go?
Yeah. But see why this is done. This blast furnace method is actually a commercial synthesis. See, you need for some purpose, you need ultra pure iron. For some purpose, you need some impurity. Means some, see, you have seen the brands there. Correct. In the market, you can see different brands. So, and different quality of iron. So you can also use a cast iron, not a pig iron. Pig iron is not that much good. Okay. Cast iron can be used, and even wrought iron is the good. Okay. So that can be used. Some builders or else some purpose, some experiments or else some dealers want that cast iron. So which is a cheaper method, cheap, which is available for cheap. Correct. So therefore we are using this method in the commercial. Is this clear, Muralidhar?
Yeah, yeah.
Okay. Otherwise, at a stretch, if we heat, we'll get the purest form and it is more costly. When anything is available in the pure form, its rate is more. Correct?
Yeah.
Yes.
I
So
mean,
students, yeah.
wrought iron, what and all things are not there. Like from pig to cast, it becomes 4 to 3% of
3%.
carbon.
Yeah.
Like
Here,
that.
students, carbon content you can remove. Carbon content. If some other metal will be there, then some other metal means not in the major excess, major quantity. In the small quantity, that you are helpless in this case. Okay. So you have to go for the fourth process. This is an incomplete process, means only a third step. Is this clear? Yes. Now,
And
wrote,
carbon
yeah.
removed, ma'am, in wrought.
What?
In wrought iron, carbon composition is not there only, ma'am.
Yeah, it is there actually. 1% carbon will be there. Okay. So all those can be removed in the fourth step. Okay, yes. Now wrought iron is the commercially purest form. Students, write down this. Wrought iron is the commercially purest form of iron. Students, here once again, wrought iron composition, carbon content, it depends upon the situation or else experimental condition. In some cases, you may even get 2% of carbon. Okay. Later at the end, what we are using now, so that you have to subject that ion to the fourth stage. Yes. That wrought iron shows almost all metallic character. Okay. You can make a wire, you can make a sheet. Correct. Okay. Almost all metallic character. Yes, students, so this completes metallurgy chapter. Okay. So then practice on the workbook problem.
Ma'am, fourth process.
Fourth process, no. So yeah, that fourth process we have already studied, refining process. And yes, students, yes, Anika, we have studied only three. There iron will not come. For iron, another thing is there, that you can go for vapor process. Vapor phase refining is there, that we are not discussing that one now. Okay, so vapor phase refining is the another technique. Refining technique can be used for iron. Okay, so that will study it in second PUC.
Okay.
Okay, yes. Students, just go through those things once. Okay, and if any doubt is there in the workbook part, you can ask. Okay, students, shall I keep test on the mole concept this Saturday? No. Satvika, no. That is the character of a student. Huh? So what teacher has to do, should not ask any question that shall I keep. No, I will keep. Huh? Yes, students, and now you take 5 to 10 minutes break. Keep it on Monday. We'll check. Monday, ma'am, please. That type of answer will come. If I say, if I ask some question, no answer. If you want a break, yes, so many messages will come. If you want to shift the exam, yes, my chat box is full. See here. Monday is physics. Okay. Yes, students, so from next week onwards, so there is a shift in the next week, or else after that, you just check your classroom, this one calendar. Okay. So there will be a shift in the classes. Okay. Physics class will be there on Tuesday from next week onwards. Next week, or else in the from the November first week, that I will arrange. Okay. So these classes will be shuffled. Physics as well as chemistry class days are different. Okay, students, now in my watch it is 35, so I'll come at 45. Okay, I'll start new lesson. Yes, students. Students, take a break, 10 minutes break. Okay, yeah. Students, come back. Keep your videos on. Students, did you study chemical bonding early? Here, maybe in the 9th or else 10th, 8th.
Ma'am, your voice is very low, ma'am.
Ninth, ma'am.
Students, did you study chemical bonding? How ionic bond is formed, how
Yes,
We
ma'am.
learned
In
covalent
in
bond is
ninth,
ninth,
ma'am.
formed.
ma'am.
That you
Ninth.
have studied, right?
Yeah.
Yes, ma'am.
Okay, so today, and what about the bonding, sigma bond, pi bond? Did
No,
you
we did
study
not
all
No,
that?
learn
ma'am.
about
That's
them.
You did not. Okay. So what about the shape of S, P, D, F?
That you
You
only
studied?
said, ma'am, the
yes, ma'am.
other day. You only showed the pictures.
Okay. This time, right? This time.
Yeah,
Yes.
yeah.
Yes. Students, 1 minute. Did I share this one? No. Yes, students, the last chapter of this unit is nothing but chemical bonding. A very small topic. Today we'll glance all the things, students, okay? So that you have studied in the previous. Students, keep your videos on. Amit, yeah,
Yes,
concentrate
ma'am.
here. Yes, concentrate here, okay? So just glance all the things, students. You know the periodic table, correct? And you know the most of the time, see, coming to the bonding, there are two types of bond. One is ionic and one more is covalent, majorly. Okay, so there are different other. You have even hydrogen bond as well as coordination bond also. So yes, that we'll study now. Now coming to this chemical bonding, so you can expect or else you can observe some bond, ionic bond in metals. Okay, S block as well as some element from P block, when they combine with each other, at that time you can observe ionic bond. When there is a bond between major P as well as some minor particles or else element from S, for example, carbon as well as hydrogen, there you can observe sharing of electrons. So that is nothing but covalent. Okay. Then there is one more type of bond. So that is nothing but hydrogen. Students, do you know anything about hydrogen bond?
Yes, ma'am.
Yes.
Yes, ma'am.
What is that hydrogen bond? Hydrogen bond means it is a bond between hydrogen as well as more electronegative elements. Okay. So that is nothing but hydrogen bond. So then third type of bond is nothing but coordination bond. So what do you mean by coordination bond? Do you know anything about this? I think in
Yes,
the
ma'am.
volume
It's
one,
a
I have
it's a
explained something.
covalent bond in which only one element gives all the electrons necessary.
Yes, it is not a element. It is a group of two atoms. Okay, so that is called a ligand. Okay, that is called ligand. Students, I don't know. Amit, are you concentrating? It seems to be
Yes, ma'am.
talking. Yeah. Okay. Students, I'll glance all the things. You see, you take ionic, right? All these points first, okay? Ionic bond. So we have to start it from the basic. You just recall all the points that you have studied. Ionic bond means a complete transfer of electron will be observed from one metal to another metal, or else from one element to another element. Okay, so that is best definition. So for example, you take a NaCl. Yes, there is a ionic bond between sodium as well as chlorine. So this bond is nothing but ionic bond. Why? How this ionic bond is formed between these two? So sodium atomic number is equal to 11. So and chlorine atomic number is equal to 17. Sodium is stable at a 10th electron. If you write electron number is equal to 10, then it will attain noble gas configuration of neon. Correct? This chlorine, if it gains 1 minute. Yeah, this chlorine, if it gains 1 electron, then it will attain argon configuration. So it is more stable. Correct? So now it donate electron. So this sodium, it donate one electron and it becomes Na plus. That complete one electron which is released from Na will be shifted to chlorine. Okay, will be shifted to chlorine. So that chlorine gains one electron. Okay, that chlorine gains one electron. If it gains one electron, okay, it is stable at 18. Correct? If it gains one electron, it will become Cl minus. That means one electron which was there in the sodium was completely shifted to chlorine, and this type of complete shifting of electron, if you observe the bond between this type of cation as well as anion, or else these two elements are nothing but the bond which is present between these two elements are nothing but ionic bond. Is this clear, students? This process is clear, right? Now, students, next step is nothing but next bond is nothing but a covalent bond. Next one is nothing but covalent bond. What do you mean by covalent bond? Covalent bond is nothing but here bond is formed by sharing of electrons. Okay, bond is formed by sharing of electrons. So that means first this here you have to concentrate on the Lewis symbol, Lewis dot symbol. Okay, so this I have explained in volume 1. Correct? Do you remember? No
Yes, ma'am.
response. Yes. Okay. Lewis dot symbol. Students, let me take a carbon. Yes. Tell me the Lewis dot symbol of this.
4 dots.
4 dots.
Okay. Yes. So 4 dots. So why it is 4 dots? Because if you
Valence
write
electron.
the electronic configuration, it is 1s2, 2s2, 2p2. Correct? So valence shell contains 4 electrons. Valence shell contains 4 electrons. So therefore you have to write carbon and then put 4 dots. That means this carbon has the capacity to form 4 sigma bonds. I will explain what is sigma and what is pi, etc. Students, now you take an example of methane, that is CH4. So how much electron, 1 minute, how much electron will be there in hydrogen? Only one. Correct? So now what is the Lewis dot symbol for hydrogen? So that is 1. Okay, so now how this bond is formed? So this is a best example for covalent bond. Students, you write carbon in the center and then write one hydrogen here, one more hydrogen here, one more hydrogen here, and one more hydrogen here. And this hydrogen, its Lewis dot symbol is like this. So one dot. Amit, you're talking, I think so. Yes, so one more hydrogen is there. So one more electron. From this hydrogen, one more electron. From this hydrogen, one more electron. Over? Yes. Then what is the Lewis dot symbol for carbon? So it also contains 4 electrons. So put that electron in the form of a dot. So this is the Lewis dot symbol for methane. Students, one bond means always there must be 2 electrons. Okay, one bond means 2 electrons. So you join all these things. Okay, so you will get 4 single bonds, sigma bonds. That means it is the best example for covalent bond. What do you mean by this covalent bond? So there exists a sharing of electrons. Correct? Correct. Sharing of electrons between this hydrogen as well as this carbon. Students, how this how these elements share their electrons? Or else, is there any particular procedure for this? Is there any particular method for this? Yes. See, always remember, students, in the periodic table, if you have hydrogen or else helium, these two elements must obey doublet rule. Okay, must obey doublet rule. And remaining all elements, okay, remaining all elements must obey octet rule. Is this clear? Okay, must obey octet rule. Why doublet? Doublet means it is 2. Okay, so doublet rule means 2 electron must be there, 2 electron. And then octet means it is a 8 electron. Is this clear? Why it is doublet, students? Hydrogen as well as helium, if you consider, its size is very, very small. Okay, its size is very small. So therefore, what happens? Size is very small. So what happens? You can't accommodate 8 electrons in that place, correct? It is very difficult to place 8 electron in that particular region. 1 minute, students, give me some time. 1 minute. Yes, students. Now, doublet, why it is doublet? Because the hydrogen as well as helium size is very, very small. Students, keep your videos on.
Ma'am,
Okay.
even lithium and other small element also follow doublet
Yes,
rule.
yes. No, usually helium actually. So you will study one more. Did you study anything related to the bonding as well as anti-bonding in previous?
No, ma'am, not. Ma'am.
No. Okay. So if you study that one, the order, bond order for helium, it is 0. Okay. If time is there, I will explain that one also. Okay. So usually helium molecule does not exist. So helium related compound is very, very less. Okay. But students, that lithium belongs to N is equal to 2. Correct. So there there you can get p block elements for the excitation. You will get p orbital for the excitation. But hydrogen as well as helium, if you consider, you have 1s1 as well as 1s2 electronic configuration. The next orbital is nothing but a 2s. Okay, you will not get any p. You will not get any p. If you add s as well as p, then the total count will be equal to 8. 2 s electrons and then 6 p electrons, total count will be equal to 8. But in case of hydrogen as well as helium is okay, you don't have such a example for helium. Okay, but while explaining, we will explain that for hydrogen as well as helium, you can observe only doublet. You can't observe octet because its size is very small and you have only 1s atomic orbital. So the next, if you apply energy for that 1s atomic orbital, the electron will shift to the 2s. Once again, only one box is there, right? You can't accommodate 8 electrons there. So that is the reason for lithium onwards. Okay, that means N is equal to 2 onwards. Okay, N is equal second period onwards. So lithium, okay, so lithium is like small once again in N is equal to 2. Okay, 1s2, 2s1 will be there. So the next element will contain P. If you apply energy, you can shift electron from S to P. Is this clear, Ketan? Yes. Yes, Navya, is there any doubt?
No, ma'am.
Okay. Because of that reason, because of small size or else because of 1s atomic orbital, this hydrogen, okay, this type of example is not there, but hydrogen shows a doublet. Hydrogen as well as helium shows a doublet rule, or else it obey doublet rule. That may, what do you mean by doublet rule? So if you consider a hydrogen, so surrounding of hydrogen, if you concentrate on the surrounding of hydrogen, it must contain 2 electrons. Is this clear? That is a doublet rule. Then what about other elements? Other elements, for if you consider other elements, if you apply energy for that, you will get higher excited orbitals. Okay, you will get for excitation you will get different orbitals, that is p orbital is available. Is this clear? Okay, students, all other elements shows octet rule. Means what is that? So the name, if you concentrate on the particular element, the neighbor of that element must contain 8 electrons. Is this clear? No response. Is this clear?
Yes, ma'am.
Yeah.
Ma'am,
Now you
what that neighbor means, ma'am? I didn't
yes,
understood that.
that I will explain. You consider the same example. So I'll rub this one, okay? So these are all covalent bonds. I will rub even these bonds, okay? I'll adjust here, but you have to write it once again. Don't rub the bonds there. Yes. Okay. Students, keep your videos on. So for some other lecturers, I was explaining that 10th case, he was a very good batch. And then all students will keep their videos and then they on, and they're very attentive. But what you are doing, yeah, my assumption, you are proving that, yes, ma'am, your assumption is wrong. Correct? Hmm. Yes, students, and now you just check whether this hydrogen follows doublet rule and then carbon carries, carbon obey octet rule. Yes, students, so you just write this diagram once again, or else sketch once again, Lewis symbol once again for methane. Write this first. Over. Yes. Students, now you just check the surroundings of hydrogen. So students, surrounding of this hydrogen means the bond between hydrogen and as well as carbon means it includes 2 electron. Is this clear? This is the surrounding of hydrogen. So whether hydrogen obey doublet rule? Yes, 2 electrons are there. What is the doublet rule of this hydrogen? So that is nothing but this one. What is the doublet of this? This is the doublet. What is the doublet of this hydrogen? This is the doublet of this hydrogen. Over? Okay. So here 4 hydrogen atoms are there. All 4 hydrogen atoms obey doublet rule. What about the carbon? Octet rule. But students, I can see only 4 dots here. How can I write it as 8?
It is sharing, ma'am. So if
One from
hydrogen
hydrogen
takes
also,
even
each.
carbon will.
Yes, it always, see, this is called covalent bond. See here, sharing takes place, right? So therefore, the surrounding of carbon is equal to this much. This is the surrounding of carbon. Correct. First electron, second electron, third electron, fourth, fifth, sixth, seventh, as well as eighth. That means the surrounding of carbon contains 8 electrons, means it obey octet rule. Is this clear? So now covalent bond as well as, okay, ionic bond, there is no confusion. Covalent bond means there must be a octet rule in almost all the molecules. Okay, is this clear? So somewhere in the structure, so I will write carbon triple bond with the oxygen, or else carbon double bond with oxygen. Why it is double bond as well as why it is triple bond? What's a Lewis dot symbol for oxygen? How many dots?
6 dots.
6.
6 dots. Okay, carbon is equal to 4. Correct? So now carbon as well as oxygen, if you consider carbon, Lewis dot symbol is dots are nothing but 4. Here for oxygen, dots are nothing but 6. So you have to balance it, right? Both carbon as well as oxygen must obey octet rule. Okay, so to obey, that's a you write a general formula. Okay, so general formula means you take a carbon and then write oxygen here. Okay, put one bond, single bond, and then try to obey. So whether you want to practice that, just for an example. Okay, so you write carbon 1 2 3 4 and one oxygen 1 2 3 4 5 6. Put one line, students, one line. Put one line means one bond. Now you just check the sharing. Check the sharing. Is it possible to, okay, so what is the surrounding of this hydrocarbon? So surrounding of hydrocarbon is nothing but this much. Is it true? Yes, it is true, but is it right? No. 1 2 3 4 5 6 electrons are there, so it is wrong. Okay, now in this case you take the surrounding of this oxygen, students. Surrounding of oxygen is nothing but this much. 2 6 1 7, total 7 electrons are there. Here 6
Excuse me,
electron, here
ma'am.
7 electron. Yes,
Ma'am, there
But
should
it
be.
did not bond the second one more electron in the carbon neighborhood, right? So how did you increase?
Yes, no, I'm checking now. So I know this carbon has 4 electrons and oxygen has 6 electrons. So I don't know anything about that, because yes, I know something, but initially what I had to say, tell, yes, I don't know anything. So first put one line over. Yes, so what I came to know, yeah, both carbon as well as oxygen does not obey octet rule. So therefore this is not the structure of carbon as well as oxygen, or else carbon monoxide. Is this clear? Yes, you arrange, go for the next one. So you arrange this oxygen as well as carbon, put double line here, put double line. Okay, so here one electron, here also one electron, here also one electron, here one more electron, and then arrange these two. And then how many electrons are remaining here? That is equal to 2. Okay, is this clear? So now go for the surrounding, count the surrounding like this. Okay, this is the method to write the structure. Students, and now tell me, any problem is there in the structure?
Carbon
Yes.
is not
Carbon
following
Carbon
don't
is
octet.
follow
Carbon
octet
does
rule.
not obey octet rule, but what about oxygen?
It follows.
It obeys.
Is this clear, students? So this is the method to write the actual structure of the compound. See, somewhere I will write, okay, well, I'll write the general one, A as well as B will be there. Somewhere I will write single bond. And somewhere I will write a triple, double bond. And somewhere I will write a triple bond. Did you get the meaning? Why I have to write single bond? Why I have to write a double bond? And why I have to write a triple bond in
Trial
particular
and
element?
error.
Yes. Trial and error
Why
means,
don't
no,
we have
yeah,
4 bond, ma'am? Like 2 carbon bonded 4 bonds.
yeah.
It is too much to ask from an element.
Yeah, like this
Yes,
type
ma'am.
of a bond is not there in chemistry. Okay, so
Why, ma'am?
see, if you write, yes, I will tell. See, if you write carbon and then if you write 4 bonds, tell me the another compound like this.
Carbon, ma'am. Yes, ma'am.
Carbon.
Carbon, you can't write any other element, right, Keaton?
Yes, ma'am.
Not at all. You can't write hydrogen, you can't write oxygen, or else you can't write 118 elements are there, right? Okay, leave so remove this carbon. You can't write any 117th element next to this bond, 4 bond. Correct? Yes. Carbon. Tell me the name of this
Ma'am,
compound.
silicon, ma'am.
Silicon, you want to connect it to, okay. Silicon, okay. Yes, what is the name of this bond? How
Carbon
to?
family can join, no, ma'am.
Yes, a carbon family. Yes, 14th group. Yes, so what is the name for that? How to
Ma'am,
name
that
this?
I'll give something, ma'am.
Okay. Yeah, what name you will give? So the compound. Okay, so it is a highly unstable compound. So yes, Keaton, there is an opportunity for research. Yes, means you can complete your master degree, or else you can go for this integrated PhD, or else PhD. You can search this, and definitely, if you do this one, you will
There may
get
be a
Nobel
Nobel
Prize.
at stake.
Yes, Nobel Prize will be given, at least in chemistry. That is for my from this one, Karnataka student. Okay, but this is highly unstable, students. Just after studying octet rule, I can't write the compound like this or else like this. There are different rules, students. Till here you have studied only octet. Okay, you know how to satisfy this by 8. There are some other rule. Okay, so VBT theory is there, crystal field theory is there. Okay, so VSEPR theory is there. All these theory, I will explain all this theory in this chapter. So at the end of the chapter, Keaton, you have to explain, is this possible or else is this stable or not? Is this clear?
Yes, ma'am.
Yes. Yes, you note on this. Okay, there is opportunity. Students, now you came to know how to write the bonds. Okay, why it is single bond, why it is double bond, when to write a triple bond, etc. Correct? Correct? Yes. Everywhere you have to satisfy the octet. Yes, students, if you satisfy octet, there are some species in chemistry. Okay.
Can the octet rule be broken?
Yes.
Exceptions are there.
Exceptional will be there in chemistry. See, in this class, it is there, means it is in chemistry also, it is there. Okay. So you can observe some elements which are some compounds which are stable with odd number of electrons. Students, if any, see, you consider carbon monoxide or else carbon dioxide or else methane, etc. If you find odd number of electrons in that, can you satisfy 8 rule, octet rule? No.
No.
But there are some examples where you can observe where you can observe the stability of that particular compound with the odd number of electrons. Okay. Then you go for the, what is the valence of sulfur?
6 oxygen family.
Oxygen family. Okay, double.
6.
Okay, oxygen is, no, valence I'm asking. Double
Two.
bond. Okay, double bond. Usually after oxygen, you will write double bond, right? Correct?
Yeah.
After nitrogen, what you will write? A triple bond you will write, right? So
Yes,
these are
ma'am.
all some rules are there. It's a valency of that particular group. But this high sulfur, sometime it shows a double, sometime it shows a 6. Okay, that means, see, general rule is nothing but you have to keep your video on. That is how you have to obey, satisfy the octet rule. Okay, but there are some species, okay, so they keep their video off. That means odd number of electron will be there, odd number. Okay, odd number of electron, even though if it contains odd number of electron, that compound is stable. That type of compound is also there. Okay, then there are some species where you can observe expanded octet. Okay, expanded octet. So this is also possible. Okay, so usually it is observed in sulfur compounds. Is this clear? So exceptional cases are there. How it will be expanded, etc. We'll study it in first PUC. Okay, yes. Students, and now where we are, yes, over. Ionic compound is over, ionic bond is over, covalent bond is over. Students,
Can you show
yes.
carbon monoxide gives that structure?
Yeah, you would have carbon monoxide. Yes, so
Yes,
tell me. Write a triple bond.
Carbon is 7, no, ma'am, then.
Carbon is 7.
Oxygen don't follow, ma'am.
Oxygen don't follow. Then how to write this one?
It cannot exist.
Huh? You can't
It's
say like that,
unstable.
right? Yes, you try. Oh, yes, it is a homework for you. Okay. Huh? You try like this. Yes.
ma'am, we won't get no, ma'am.
It is possible. You just check. Students.
It is possible from octet itself.
Yes, octet only, from octet only. Okay. You can write that. Students, one more rule is there here. I'll give the clue.
One from the
Just-
oxygen goes to the carbon.
One from the oxygen goes to the carbon. Oh, like that. Oh, sharing. So that sharing is not there. Okay, that type of sharing is not there. Students, I will try, I will tell you one thing. Students, if you are not able, so this is the advanced method, Cosil postulates. Okay, this is called Cosil postulates. So you will study it in PUC, first PUC. Students, according to this rule, Cosil postulate, he says that if you are not able to satisfy that particular compound by octet rule, then you have to add extra electron.
From where will you get that?
That from the pocket. Okay, so you have to add. See, if you write a CO3, yes, can you tell me the structure of CO3?
That doesn't exist.
That is ion, ma'am, CO3 2.
Yes, so why I have to write it as a 2 minus? Why I have to write it as 2 minus?
So that it obeys.
It takes 2
octet.
electron from
Why
the
it
pocket.
is, why it takes, yes, from not from the pocket. It depends upon the situation. Okay, so if you split the calcium carbonate, so you can get that not from calcium carbonate. So carbonate radical will be there, right? So from there I can write it as CO3 2 minus. So but students, can I write as Lewis dot symbol for this? If you solve this one, similarly you can solve carbon monoxide. So you write
Ma'am,
carbon.
if you have the freedom of adding the electron, you can make any compound.
Yes. Therefore, I'm able to
Stability
prepare.
should be there, ma'am.
Yes, stability will be there. Stability will come whenever you satisfy it by 8. Okay.
And then C double 4 bond with C, it's also stable, right?
Okay, C bond with the 4
Yes,
C stable.
yes, ma'am. It
Yes.
should be stable, ma'am. It follows octet rule.
Yeah, I will search this one. Okay, I don't know anything about this. So till my chemistry study, I did not search this type of problem. Means situation. So I'll check out why it is not
Ma'am,
there.
not like that.
Yes.
If we go on keeping adding electrons, we can make means anything, any compound with any element.
Yes, any compound with any element can be prepared according to octet over Shashank. Then the next theory comes related to the stability, that is VBT. So the next theory comes related to the stability, once again VSEPR. Next theory will come, that is MOT, molecular orbital theory. So you have to satisfy the structure or else stability based on all these postulates. Okay, now students, we are in the first standard of this chemical bonding. We'll study each and everything. So by the end of this chapter, you will come to know VBT theory, VSEPR theory. MOT is not there. If you want, I will explain. Okay. So at that time, you will come to know, or else the complete idea you will get the structure. Why it is not possible to have this type of bond. So that answer is also there, Keaton, at the end. Okay.
Excuse me, ma'am.
Yes, Anika.
Ma'am, in carbon monoxide, can oxygen share 4 electrons to 2 electrons from carbon? That.
No.
This
Yeah,
is
yes,
not
Mix,
right,
bar
right,
game.
right.
ma'am.
Yes, students,
In
1 minute,
CO,
1 minute, 1 minute. I will complete this rule. Students, if it not possible to attain, satisfy this 8, so either you have to add 2 electrons, okay? You add, not 2 electrons, okay? You add electrons till it satisfies 8, okay? Or else sometime if it carries 9 electron or else 10 electron, at that time you have to remove the electron from the system, from the
Ma'am,
total
can you
system.
show one example, like how to add or remove?
Yes, you have to help me because you know the Louis dot symbol, right? I don't know anything. I will write like this. Yes, arrange this one. So I have written like this, right? You have to arrange this one and then help me to write the structure. 3 oxygens as well as 1 carbon must satisfy the octet rule.
one
For one
one
oxygen, we can give
double
2
bond.
electrons, and then we can do what we did to carbon dioxide.
Yes, I will write carbon here. Okay. Then how many electrons I have to write? Think, students. See here, if you
Ma'am,
want to
single bond to 2 oxygen and double bond to 1 oxygen.
single bond. Did you try that?
Ma'am, or you can give 6 electrons to carbon.
6 electrons to carbon.
Carbon.
Carbon. There is no space, Muralidhar. Okay.
Then you said we can add, right?
You can add to the total system, not to the carbon. This one carbon for 1 oxygen you can't add. Okay. Either you have to remove electron from the total system, or else you have to add electron to the total system, not from the single element. Okay. So you write the concentrate on the structure of carbon 2s2, 2p2. Already 2 electrons are there in one 2s2. Okay, I'll remove that. Then 2p2. So you can fill only 3. Sorry, 2 more. 2 more. Okay, is this clear?
4
Yes.
no, ma'am. 2p6 maximum.
That is a pairing. Pairing. Okay. Yes. Now tell me. So yes, Keaton gave this
One more
idea.
oxygen, ma'am.
One
Single
more
bond.
oxygen. Okay, one more oxygen with a single bond. Yes. Now you just write all the electrons. 1, 2, 3, 4. Yes. Carbon Lewis dot symbol is done. So that is 1, 2, 3, 4. 1, 2. Okay, for this 3, 4, 5, 6. Here only one I have written. 1, 2, 3, 4. One I have written. So it is 1, 2, 3, 4, 5. 1, 2, 4, 6. Yes. Now, is this satisfied?
And then add 2 electrons.
Wait. So you see the surrounding of this oxygen. This is the surrounding of this oxygen. This is the surrounding of this oxygen. Tell me whether this oxygen satisfies 8 octet rule.
Yeah.
Yes, ma'am.
So this is 8. Okay. So what about this?
No.
No.
No. How many electrons are there?
7.
6.
Ah, 6.
7.
7.
Ah, yes, 7. So how many electrons are there here?
7.
7.
7.
Now what about the this one carbon
8.
surroundings?
8.
Okay. So this is 8. Over. What is the problem?
Add 2 electrons.
Why I have to add?
7,
Adjust
7,
that
ma'am.
one. Adjust that one. If you adjust it in any other way, can you write this one? Can you satisfy octet? No. So therefore, to the total system, you add 2 electrons. So therefore, you are writing CO3 2 minus. Did you get the meaning? Okay.
So we don't choose where we add it. We simply add it.
Ah, so you can add it to this oxygen or else to this oxygen or else to this oxygen. It depends. So there is no compulsory that you have to write a single bond here, you have to write a double bond here. Okay, so therefore,
And how does
select
the
the
carbon decide to which oxygen it's going to do a double bond with?
yeah, that is little difficult to answer. Okay,
So,
so
ma'am,
yeah,
will all the will the sharing take place at the same time, or if it is not, then it can go to one oxygen and then the same electron
no,
can
no,
go to another.
no. That you can't do, right? Can you convert that concept to a experiment practical situation? Is it possible? No. Okay, so it cannot. Okay, so you are telling that you're asking that this carbon once it shares a bond with this, okay, 8 is it satisfies this oxygen first with 8, and then it is satisfied this oxygen with 8, and then it is satisfied with this oxygen 8. But students, I want this CO3 2 minus as a together lump in the form of a lump sum, correct? So if I say, imagine this is a calcium carbonate that I have. If it keep on changes the bonding, then what conclusion I have to give? I have to write a textbook and I have to teach it to the students. Correct? What conclusion I can give? See, yes, Satvika, your question is reasonable. So because this benzene is there, right? So it plays like that. Correct? It goes on. So single bond as well as double bond is there, right? It goes on shifting. So you can write a single bond here, double bond here, single bond, then double bond. Sorry, I can write like this, or else I can write like this.
Why can't you do the same thing with CO3 2 minus?
CO3 2 minus. Yes, answer is there it in the sigma as well as pi bond. I will explain. Okay, so how sigma bond is formed? How the pi bond is formed? Yes, yes, yes. So these single bonds are nothing but sigma bonds, and then this double bond is there, right? This is a pi bond. I will explain how this sigma as well as pi bond is formed. Is this clear? Is it okay? Students, how to write this benzene structure then? You can't write like this.
Put a
Okay.
circle.
Yeah, put a circle. What is the meaning of that circle? So you may get a double bond everywhere. Anyway, if you write a double bond here, then the alternative position is a single bond. Single bond, double bond. Okay, alternatively it shifts. But here, that type of facility is not there. You can expect pi bond in only one case. Okay, if it keep on changes, that is once it satisfy one oxygen, another oxygen, third oxygen, okay, it is impossible to explain the stability of that particular compound. Is this clear, Satvika? Okay, to decide stability, there must be a particular bond. Say for example, friends will be there for you, correct? So imagine Satvika as well as Anvita are the best friend. If Satvika keep on changes her friend circle, then how to decide? Okay, teacher like me, so I will say, okay, Satvika and Anvita are best friend. Okay, if you keep on changes your friend circle, then how to decide which one who is your best friend? Correct? It is very difficult to judge on that. Correct? Take a decision on that particular thing. Okay, is this clear? Here also same thing. Yes, students. Now where we are now? Yes, similarly, yes, this is not completed, right? So you add one electron to this system. Add one more electron to the system. So now this becomes 8 and this also becomes 8. What you have to do? Write CO3 and write 2 minus. Over. Correct? Correct. So this is the thing. Sometime what happens, students, from the system, so there you may get, in one place you may get a 9 electron. Okay, so imagine like this. Okay, in one place you got a 9 electron. At that time what you have to write? You have to remove it. Okay, you have to remove it. At that time what sign you have to write? A plus. So after writing some ion, you will write it as plus, right? Why it is plus? That is because you have to remove electron from the total system. Is it clear? Okay, yes. Now, using this technique, students, this is a homework. Carbon monoxide, you decide how many bonds are there. Not a single bond.
Ma'am, triple bond, ma'am.
Yes, it is triple bond. Okay.
Should add one electron.
No. CO, is there any CO minus? No. Is there
Ma'am,
any CO
from
plus? No.
ma'am, carbon takes an electron from oxygen.
Yes, Ketan, tell me.
Ma'am, oxygen have 9 electron and carbon have 7 electrons. So it takes from oxygen.
9 electron in oxygen?
Yes, ma'am, after bonding. So it takes one.
Okay, I'll write like this, okay? Yeah, I will arrange this one in this way. Okay, over 3, 3, 6 over, right? So the surrounding of this contains a 6 electron and the surrounding of this oxygen also contains 6 electron, but I can write a 2 electron here. And if I write a 3 electron, then it becomes a 9, okay? Octet rule will be crossed. Yes, you write 2 electron here. Okay?
How is that possible, ma'am?
Yes, all arrangements are
Ma'am,
possible
this was
based
what
on
I
the...
said, ma'am.
Oh, Muralidhar. Okay, correct. Okay.
Okay.
Based on the particular situation, not always, students, not always. Not always. Based on the particular. So you have to study first causal postulates. It has its own rule. Okay. So you have to, if triple bonds are there, or else more than, sorry, that is called super bonds. Okay, super bonds, super triple bonds as
Won't
well as
this
double
become
bonds.
ionic bond? Like there is transfer of electrons, right?
No. If you transfer, see, okay, one electron you have transferred. What about the remaining that you have shared?
It is not, neither ionic nor covalent.
It's
No, it is
both. It's
completely
both,
covalent.
ma'am.
It is completely covalent. It is not both. It is not both. It is completely covalent. So that electron is transferred to the carbon, but remaining electrons are shared. So we are always giving, see, in general, what we'll do, we'll give
How
importance
do
for
we
the
know to
majority.
put it as a triple bond or a double bond for carbon monoxide?
Yeah, that is a trial and error method. Okay. So
No, can't we
initially,
just put two bonds and then distribute the electrons so that still the octet rule is followed?
okay, 2 electron you put, and then you know the rule here, 2 electron you put, right? You write here, 2 more electrons here you write, and then take the surrounding of this. 2, 4,
No,
6, 8. And
you
take the
give two
surrounding of this.
electrons to carbon.
From where? From pocket. At that time, what happens? CO2 minus, which is highly unstable.
Okay, so your objective is to minimize that charge.
Not
What you give
minimize
from
the
your
charge.
pocket.
Not minimize the charge. You have to make it stable. You can add any
How
number
to
of
know, ma'am,
electrons.
it's stable or not?
Yeah, I understand,
Okay.
ma'am. How to
Yes.
know whether it is stable?
Okay. So if you are that much interested, I will discuss causal postulates in next class. Okay. So at that time you can decide. Okay. Is
Okay,
it
ma'am.
okay?
So next class test is not there.
Okay. Then next week.
No,
Okay.
ma'am, we are very eager to learn the
Yes,
causal
ma'am.
postulates.
Yes, ma'am.
Okay. I'll decide it later. Okay. Yes. Since you are not responding too much in the class. So, so what is this? Okay. There is no quiz. Okay. Yes. Uh, yes, first preference will be given to test. Based on that,
Ma'am, please, ma'am.
causal postulate will give a next second
That's
preference.
important, ma'am.
Which one is important?
Causal postulate, ma'am.
Fourth chapter is important, or else the second chapter is
Fourth,
important?
ma'am.
Fourth, ma'am.
Fourth, ma'am.
Okay, we'll decide. Okay, so now it is time up. So I'll stop this class. Okay, we'll discuss causal postulates, and based on that, okay, different rules are there. Based on that, we'll study how to arrange the structure of a compound. Okay, is it okay?
Yes,
Yes,
ma'am.
but check Schoology regularly. Okay. Yes.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Yes, that
Thank you, ma'am.
yeah, mole concept DPP. I will post it. Okay.